Hello, students, and welcome. Today, we are going to build a strong understanding of two very important topics in sound, its speed and its reflection. Let's quickly look at the roadmap for our lesson today. We will start by understanding the speed of sound, then see what factors affect it, and do some calculations. After that, we'll move on to reflection, echo, and reverberation, look at some practical uses, and finally, we will do a quick recap. Okay, so let's dive right into our first section. What exactly is the speed of sound? Let's start with a question you may have thought about. I'm sure you have all experienced this. During a thunderstorm, what do you notice first? The flash of lightning or the sound of thunder? You always see the lightning first, isn't it? Why does this happen? Well, the answer is actually quite simple. It's because the speed of light is much, much faster than the speed of sound. The light from the lightning flash reaches our eyes almost instantly, but the sound of the thunder, well, it takes its own time to travel through the air to reach our ears. This shows us that sound travels at a specific, finite speed. And this brings us to a very basic formula that I'm sure you all remember. Speed is simply the distance traveled divided by the time taken to travel that distance. This relationship, speed equals distance divided by time, is the foundation for all the calculations we will do today. Now, an important question is the speed of sound always the same, or does it change? Let's find out what factors can affect the speed of sound. So, the speed of sound is not a constant value. It actually depends on the properties of the medium through which it is traveling. And there are two main factors we need to consider. First, the state of the medium, that is, whether it's a solid, a liquid, or a gas. And second, the temperature of that medium. Now, let's look at some actual values. This table shows the speed of sound in different substances at a temperature of 25 degrees Celsius. Look carefully. In a solid like steel, sound travels at a very high speed, 5,960 meters per second. In a liquid like water, it is much slower, around 1,498 meters per second. And in a gas like air, it is the slowest, only about 346 meters per second. The difference is huge, isn't it? So why is there such a big difference? The reason is all about the particles in the medium. In solids, the particles are packed very, very closely together. So when one particle vibrates, it quickly makes the next one vibrate. The energy is transferred very fast. But in gases, the particles are very far apart. It takes much longer for the vibration to travel from one particle to the next. That is why sound travels fastest in solids and slowest in gases. The second factor is temperature. The relationship here is quite straightforward. As the temperature of a medium increases, the speed of sound in that medium also increases. Think about it. When the air is warmer, the particles have more energy and move faster, so they can pass on the sound vibrations more quickly. This means on a warm, sunny day, sound travels a little bit faster than on a cold winter day. Okay, now we will look at how to solve some numerical problems related to sound waves. Now, this is a very, very important formula that you must remember. It connects the speed of a wave, which we represent with the letter V, to its wavelength and frequency. Wavelength is represented by the Greek letter lambda, and frequency is represented by the Greek letter nu. The formula is speed equals wavelength multiplied by frequency. Please make a note of this. Let's work through an example problem together. A sound wave has a frequency of 2 kilohertz and a wavelength of 35 centimeters. The question is, how long will it take to travel 1.5 kilometers? Right. The first and most important step is to convert all the given data into their SI units. So 2 kilohertz becomes 2,000 hertz, 35 centimeters becomes 0.35 meters, and 1.5 kilometers becomes 1,500 meters. Always do this first. Now we can calculate the speed using our formula. Speed equals wavelength times frequency. So speed is 0.35 multiplied by 2,000, which gives us 700 meters per second. We have the speed and we have the distance. Now we can find the time using our basic formula. Time equals distance divided by speed. So that's 1,500 divided by 700, which gives us approximately 2.14 seconds. It is quite simple if you follow the steps carefully. So up until now, we've been talking about sound traveling forward. But what happens when a sound wave hits an obstacle, like a wall or a big building? Well, it bounces back. And this bouncing back of sound is what we call reflection. Let's explore this idea now. Now, this might sound familiar to you. Just like light, sound also follows two very specific laws of reflection. The first law says that the angle of incidence is equal to the angle of reflection.
And the second law says that the incident wave, the reflected wave, and the normal all lie in the same plane. These are exactly the same laws that you have studied for the reflection of light.
One of the most common effects of sound reflection is an echo. An echo is simply the repetition of a sound that we hear after the original sound is stopped. But there is a very important condition for an echo to be heard. The reflected sound must reach our ears at least 0.1 seconds after we hear the original sound. Why? Because our brain holds onto a sound for about 0.1 seconds. This is called the persistence of hearing. If the reflected sound comes back too quickly, our brain can't distinguish it from the original sound. So this time delay of 0.1 seconds leads to a minimum distance needed to hear an echo. Let's calculate it. If we take the speed of sound in air at 22 degrees Celsius as 344 meters per second, then the distance the sound must travel is speed multiplied by time. That's 344 times 0.1, which is 34.4 meters. But remember, this is the total distance to the reflecting surface and back again. So the minimum distance from the surface itself is half of this. 34.4 divided by 2, which is 17.2 meters. This is a very important value to remember. Now, it's very important to understand the difference between an echo and another phenomenon called reverberation. An echo, as we just learned, is a single, clear, distinct reflection of sound. You might hear this in a mountainous area. Reverberation, however, is caused by multiple reflections of sound. Imagine you are in a large, empty hall. When you speak, the sound bounces off the walls, the ceiling, the floor again and again. This persistence of sound is reverberation. It's not a clear repetition, but a sort of prolonged sound.
Okay, so now that we understand reflection, let's look at how we use this principle in some very practical, everyday applications.
Look at a megaphone or a musical horn. They have a specific cone shape for a reason. This shape is designed to cause multiple reflections of sound inside it. These reflections prevent the sound from spreading out in all directions. Instead, the sound is guided and directed in a straight line towards the audience. This makes the sound much louder and allows it to travel a longer distance. We see the same principle in a doctor's stethoscope. The sound from a patient's chest travels up the tube to the doctor's ears because of multiple reflections inside the tube. Another excellent example is the ceiling of concert halls or auditoriums. You will often see that they are curved. This is done so that after reflection, the sound from the stage reaches all corners of the hall evenly. It ensures everyone in the audience can hear clearly. All right, we have covered quite a bit today, so let's do a quick recap of all the important points from our lesson. Please pay close attention to these key definitions and laws. They are very important. The speed of sound is the distance traveled by a sound wave per unit of time. An echo is a single, distinct, reflected sound, and for it to be heard, there must be a delay of at least 0.1 seconds. Reverberation is the persistence of sound due to repeated reflections. And finally, the laws of reflection state that the angle of incidence is equal to the angle of reflection. And to finish, here is a small question for you to think about. If you are standing in front of a cliff and you hear your echo after 2 seconds, which of the formula we learned today would you use to find the distance to that cliff? Think about it. We will discuss the answer in our next class.